Hey class, circumstances dictated that I had to record this lecture from a laptop rather than my desktop. So this one and the next one may be a little bit different. So if the sound is off, if it's not synchronized to the motion of my lips, I apologize. It should just be a couple of lectures. So let's jump back into the lecture notes. We should only have at most 2 more classes of them. And then after spring break, we will switch to the more practical demonstrations in the course. Okay, so we left off with Hamilton, we left off with the theory regarding the relationship between transitive paths where you're going between edges and so forth, where you can make more than a single jump between vertices, and the matrices and matrix exponentiation. Okay, so thought that was a pretty cool theorem. Alright, so now we move back into definition, and so this one is pretty straightforward. So whenever we discuss Euler circuits and paths and Hamilton circuits and paths, just keep in mind that Euler deals with edges, and Hamilton deals with vertices. Okay, so by definition, an Euler circuit is a graph, some graph named G, which is a simple circuit and contains every edge of G. So you begin and end at the same vertex in an Euler circuit, and you consume every edge in your walk. And so this is the type of circuit that you would want if you were cleaning a highway or something. So you don't want to have to double back on the same path. You want every mile traveled to be cleaning new ground until eventually you end up back where you started. So that would be an Euler circuit. An Euler path in G is a simple path containing every edge of G. So the distinction between the circuit and the graph is, in both of them you're consuming every edge, but if you have a circuit, then you end up back where you started, and if you have a path, general path, then you don't necessarily end up back where you started. But in both cases, in order for it to be of the type that Leonard Euler studied, then it has to consume every edge in the graph. Okay, so now we have our first theorem. A connected multigraph with at least 2 vertices has an Euler circuit if and only if each of its vertices has even degree. And so the example associated with this in the book is the bridges of and I forget the city, but it's a problem dealing with bridges. And so the question asked whether or not it was possible to start on one point in this park and cross every bridge and end up back where you started without repeating a single bridge. And so it was a question for lovers strolling through the park. So they wanted to know, if 2 people courting each other could just meander through and visit as much of the park as possible without having to double back, run into their chaperone or whatever. The problem under consideration, the answer was no, and so we have this condition, this if and only if condition. So if it's satisfied, and only when it's satisfied, and in no other cases, can you satisfy that Euler circuit requirement? Can you end up back where you started without crossing the same bridge twice? And so that was the answer to the question. And so that's our theorem for that. So it has to be of even degree, and that makes sense. So so if you have a vertex or whatever, and it's an island in the case of bridges, right, then you can only end up back at the same island that you started with if whenever you so you leave the first island, you begin at some destination, some point, and then you begin crossing these bridges, and the only way that you can uniquely consume each of these bridges, or to fully consume each of these bridges without repeating any one of them, is if whenever you enter some new island via some bridge, that you have a new exit, right? So each vertex has to have an entry and an exit. Every time you enter it, you need to be able to exit through some new bridge. So enter plus exit, that's 2 degrees each time you want to consume some new vertex or travel through to some new point. And so it makes sense whenever you break it down like that. And if you enter, you have to be able to exit, or in the case with that very initial and terminal vertex, if you exit, you have to be able to re-enter, right? So we would expect there to be a condition like this where it has even degree, and so Euler was able to formalize that. Okay, so next theorem: a connected multigraph has an Euler path but not an Euler circuit if and only if it has exactly 2 vertices of odd degree. Okay, so we said a path doesn't necessarily imply a circuit. And so this is exactly the same conditions that we were just discussing, except that you don't end up back where you started. And so we say, okay, well, you don't have to end up back where you started, but you can still consume every bridge if the only difference is that whenever you exit that first one, you don't have re-entry, right? Otherwise, you would need odd degree in order to end up somewhere other than where you started, right? So you only have an exit from that initial island, or you have that initial exit and then a pair of entry and exits so that you end up somewhere else. And so that first vertex has to have odd degree, and then the last one, the one that you end on but you never leave, so there's only entry and no exit, you would also expect to have odd degree. Right? So the condition for having a path that is not a circuit has exactly 2 vertices of odd degree, the initial vertex and the terminal vertex. Okay. So back to definitions. A simple path in some graph G that passes through every vertex exactly once is called a Hamilton path. And so remember, Euler, E for Euler was edges, and then Hamilton was vertices. Right? So now instead of consuming edges, we're looking at visiting vertices. Right? So pass through every vertex exactly once is called a Hamilton path. And a simple circuit in a graph G that passes through every vertex exactly once is called a Hamilton circuit. So same thing. Each vertex once is called a path. Each vertex once and ending up back where you started is called a circuit, a Hamilton circuit. And so now if we label the vertices x0, x1, all the way up to xn in the graph, then it's a Hamilton path if the set of vertices is this, right? So if we start here and then we jump to this one and then so on and so forth progressively, and if we don't have any repeats except for the beginning and the end, and then that was for the path, right? So we have n plus 1 vertices, and each one of them is distinct, right? And so I could have written I not equal to j here, right? For I not equal to j, but whatever, we just sort it here. And the simple circuit, where we visit the n plus 1 vertices, and then we end up back where we started at x0. Right. And so that's a Hamilton circuit if and only if, whenever we consider the n plus 1 vertices, x0 through xn, are a Hamilton path. Right, so that's a quick check. Okay, and so that's by definition. That's how we define it. But don't get lost in the formalism. This is just how you represent it formally. But the essence of the idea, whenever we're discussing a Hamilton path, is that you go to each vertex exactly once, and the term that we'll use over and over again is to visit them. Right? And whenever you're dealing with problems in graphs or in trees or anything else, the design pattern is called the visitor pattern. So you essentially browse through, or you iterate over the collection, and then you perform some action against that vertex, and that's called visiting it, right? So you have some function that you want to do for everything along this path, and so you end up visiting the nodes in that path. Okay, so again, it's the vertices for Hamilton and edges for Euler. Okay, so Dirac's theorem. So if G is a simple graph with n vertices, and n is greater than or equal to 3, such that the degree of every vertex in G is at least n divided by 2, then G has a Hamilton circuit. Okay, so you can treat the case for n less than 3. So whenever n is 2, right, then it'll have, so if you have two vertices, if you have exactly two vertices, and it's a simple graph, so it's not a multigraph, but yeah, if it's a simple graph and it only has two vertices, then there's only one road from A to B, and you can't get back. So you automatically have a Hamilton path if it's connected, and you do not have a Hamilton circuit, because if there's only two vertices and there's only at most one edge joining any pair of vertices, then you can't do it, right? So you can treat the case for n equals 2 or n equals 1 individually. But once you get up to 3 or more, then the condition to satisfy a Hamilton circuit, so where you visit every vertex and you end up back where you started, and it's a simple graph rather than a multigraph, right? Then in such a case, you are guaranteed a Hamilton circuit if you have each vertex in your graph with degree n greater n divided by 2 or more, right? So if you have 32 vertices, right, then if the degree of each vertex was 16 or greater, then you would have a Hamilton circuit. Then you would know that you can end up back where you started. So I want you to notice that this one doesn't claim the if and only if requirement. So whenever we're looking at the theorem for Euler paths and Euler circuits, it was an if and only if condition, where the degree was even, the degree of each vertex was even, or in the case of a path where you have at most or exactly 2 of odd degree, right? But here, it's harder to make a general statement, right? So you can have an Euler, or you can have a Hamilton circuit with degree exactly 2, right? So if you just have a ring, right, if you just drew it in a ring, then you could go in a circle, essentially. You could go from one to the next and so on and so forth in this chain, and it wraps back around to where you started. And every vertex has degree 2, and it's not a terribly interesting graph, but it works. It has a Hamilton circuit. And you would have a Hamilton path with the same thing, but you remove exactly one edge, so that you start in one location and then you end at the furthest node. And so you can have one without meeting this condition, but in order to guarantee that you have a Hamilton circuit, then you need degree n over 2. And so you start requiring a lot of edges in order to guarantee this ability to to create your circuit, visiting every node exactly once. Okay, Order's theorem. If G is a simple graph with n vertices and the number of nodes is at least 3, such that the degree of U plus the degree of V is greater than or equal to n for every pair of non-adjacent vertices U and V in G, then G has a Hamilton circuit. Okay, so this one gives you a little more leeway here, right? So over here we say that each one has to be at least n over 2. And here we say, okay, well, you can have one that's less than n over 2. So you can have one that's of degree like 3 in the case where you have 32 nodes, so long as everything that touches it has degree at least 29, right? So as long as everything else is really well connected, then you can kind of deal with these isolated nodes where there's not a lot of connections going on, right? You can deal with them so long as they're fully surrounded by other vertices that are extremely well connected, right? So it's sort of a forgiveness for an inability to meet this requirement. Okay, and so this has to be true for every pair of non-adjacent vertices U and V in G. Oh, okay, I'm sorry, I stated that backwards, right? There's not as much forgiveness in this as you would think. So it's really just an ability to kind of tolerate one or two. But the fact that it requires it for non-adjacent means that if you had two and they weren't directly connected with each other, then you would fail to meet this requirement pretty quickly. So it just allows you to tolerate them so long as they're in rapid succession of one another, so long as you're jumping directly between them. Okay. So the shortest path problems. We will end up coming back and coding this out, or coding out Dijkstra's algorithm. But shortest path, whenever you're dealing with non-circuits, is not so bad. But whenever you're dealing with Hamilton circuits, it's essentially as bad as it can be. Right? And we'll discuss that in a little bit. Okay, so shortest path problems, going from A to B in the most efficient manner. So graphs have a number assigned, so this is by definition, right, for a weighted graph. So graphs that have a number assigned to each edge are called weighted graphs. And so in the highway format, then a weighted graph, like the weight might be the speed, right? And so you're trying to, let's see, maybe it's the distance divided by the speed for that road, right? So it's essentially the time that it takes to travel along that particular path. So if you want to go from A to B, then you're trying to minimize time in order to optimize your path. In the case of network traffic, like computer networks, then the weight would probably be related to the speed of the connection, right? So fiber optic would have less resistance and would travel a little bit faster than Cat5, and that would have a lower weight, presumably, than telephone wire, and so forth. And so it can also hide additional things, right? So if you have relays along the path, then those would show up in the weight as well, so that the time it takes to boost a signal and so forth would also show up. So you can hide kind of other devices in the edge and just hide it, but account for it in some form of a weight, so that you're saying, okay, it's slower if you go this way, and it's faster or cheaper if you go this other way. Okay, so next definition: the length of a path in a weighted graph is the sum of the weights of the edges in the path. Right? So it's the total weight, or sometimes we'll call it the length. And so this definition agrees with our intuition of the length of a road trip, where the vertices in the graph are the stops made along the way, and the edges equating to the strip of road traveled between the stops. So like I said, you can measure it in time if you divide distance by the speed limit, okay? Or you can measure it in miles if you just look straight out at the number of miles between the two destinations. And if you're going by foot, then speed limit doesn't apply, right? It's miles is the only thing that really matters, the direct distance. Although you may want to add additional weight if you're trying to jump over barbed wire fences and cross private property and stuff as well during your trip. Okay. So now we have a theorem. Dijkstra's algorithm finds the length of shortest path between two vertices in a connected, simple, undirected, weighted graph. So it doesn't state Dijkstra's algorithm outright. It just by theorem, we have that this algorithm finds the shortest path. Right? And this is for a simple, so not a multigraph, but a simple undirected weighted graph. Right? Okay. So now we'll get to take a look at it, right? And if we finish the notes, then the next class, this will be the very first thing we do. We'll code this out and take a look at it. The example is provided in Java. I can't remember if there's another language, but we'll pick a different language and we'll implement Dijkstra's against that. Possibly JavaScript, possibly C, possibly C#. I'm not sure. We'll figure it out. Okay, so this implementation is provided in 4 separate files. You'll see them listed up here. Right? It'll be vertex, edge, graph, and then the main file. The first 3 Java class files define objects used in describing a graph, right? And so this is just in general. So whenever you start discussing a problem and representing it in code, in the object-oriented paradigm, where you're looking at describing things and then the methods or the actions against those things, right? Well, then the things are objects. The nouns end up becoming your classes. So when we're discussing this, right, like it seems really abstract. Okay, I got it. Graph, vertices, edges, yeah, whatever. But no, really, like in whenever you start coding it, you have a graph. So you would expect a graph class, right? You have a vertex, right? And so the vertex has these things that describe a vertex. And you have an edge, right? Or edges, right? And so you define a class that describes what a vertex is. You do the same thing with an edge. And then a graph will hold a collection of vertices and edges, right? And so it's very direct, right? As soon as you learn how to make that interpretation, to go from what we describe and how we discuss these problems in terms of how we represent them in code. And so the more experience you get, the less intimidating it'll be to go from something that you're discussing into something that you are programming, right? So begin with the nouns, right? So we're dealing with a graph. A graph is defined as a collection of vertices and edges. Perfect, we'll start there. Okay, so define the objects suitable for Dijkstra's algorithm. So a graph composed of a collection of vertices and edges. And then the 4th file is the entry point to the program and constructs the graph, then invokes solve Dijkstra to yield a solution. Okay, so a vertex, we define which package this is going to be. And so the project, I just named it Dijkstra. Right? We import array list from java.util. And then there are access modifiers, right? So you can define whether a class is meant only for the other classes and constructs that are defined in the current package, or if you intend to export it, such as the Java libraries will, right? Like java.util, they're exporting an array list. So in that case, you would make it public, but here we don't make it public. So final, right? So now we're looking at these declarations, right? So private is again an access modifier, so only the things inside this class should know that this underscore name property exists, or private variable exists. And the same thing with this underscore edges. And then this is a convention that is fairly standard, that whenever you have a private variable that is a class variable, so not something that you're defining within a function, even if it's a class function, but if it's exposed to the class and limited to the class, then you precede it with an underscore. And then final means that it'll be set once, either during the initialization and declaration part, or during the constructor, right? So final means I'll set it once, and then after that it's read-only. And so other languages will declare it as read-only. Java declares it as final, right? So private, final, then the data type, it's a string, so each vertex has a name. If it's cities, then it's a city. If it's just general vertex, it's some node, then it'll be given a letter or a serial number or something, right? But that'll be its name. And then the vertices, each vertex knows which edges are adjacent to it, or incident to it. And so we define this to maintain that collection. So now we initialize them, so the name will be whatever's passed into the constructor, and the edges will start as just an empty array list. Right? And then we expose a method, get name, so that we can print the name. We expose a method to add edges, so that as we're building the graph and we say this edge connects vertex A to vertex C, then the edge that gets created will become incident to this vertex, both A and C. Right? So we provide some means to keep track of those edges. And you'll notice that we don't provide the means to iterate the edges, right? So this, in the end, we're maintaining it, and we give ourselves the option to add on to it later. But for now, we only maintain it so that we can say what the degree is, right? Like, what is the degree of this vertex? And then another pattern that I want you to develop the habit of early on for debugging is to provide some form of two-string method. So both Java and C# by default have a two-string method that you can override in any class declaration that you make. And I encourage you to get in the habit of doing that. So there are some classes that they work, and they're static classes, and they don't actually have an instance of that object. But everything else, any type of class that you intend to instantiate, so probably anything other than the main class or your entry point, you should, if you're going to create an instance of it, then you should provide a two-string method. And the two-string method, as a rule, so you'll eventually learn how to determine exceptions to the rule, but as a rule, it'll be a summary of whatever your private variables are. What makes that object itself? What makes it unique? What defines it? And then, anything that gives you a hint as to information or state of that object, so that whenever you're debugging it, it's already available. And then I can save you the trouble of wondering, when you'll get to the point that you have to stop debugging. The answer is never. You will never be so good that you don't have to debug your work as you go along. And that's part of it, just embracing these tools that are available to you. It's an iterative process. You're always modifying it and trying to tend towards some solution. But you should acknowledge from the beginning that you are going to need little helpers like two-string and other debugging methods to help you along your way. No matter how good you are, in fact, the better you get, the quicker you will develop these two-string methods, instead of hoping that you won't need to debug it and then later on eventually grudgingly adding these. Just add it from the beginning, and you'll get fast enough that you won't even notice the time that it takes to do it. And then if you have to modify it later, so what? It takes 30 seconds or less. Right? So do get in the habit of creating these two-string methods for anything that you can create an instance of. And then we'll take a look at how to do something similar in JavaScript as well. But for Java and C#, and then it's a little more challenging in C because you define the struct, and then you have to figure out how you're going to format those strings and so forth. But C++, you would also have the ability to define an instance method like toString. Okay. So now we define the edge, right? Same package, it still belongs to Dijkstra, it's the same project. And then again, we still just want it to be internal to the package, so we don't declare it as a public class. So now the private variables, again, they're final. We define them exactly once. Right? Is going to be the name, the source vertex, the destination vertex, and it's an undirected graph. So these are just logical source and destination. But source, destination, and then weight. And the weight is known up front. So whenever we're setting up the problem, when we're setting up the graph, we already know the weight. So every one of these is final. It's all read-only. We set it once, and then it never changes. And you might be wondering, okay, well, why would I want that? And it's so that you can't mess it up, right? So when would an edge ever be moved around? You know, the answer is never. If it gets removed, it gets destroyed. And if you create something new, then it's entirely new and treat it as such, right? So, so it's not wasteful like a piece of lumber or something where you might be able to reuse it. It's all logical, and it's all, you know, it's a lot cheaper than, you know, raw materials in the real world. So immutability, this guarantee that this thing cannot be changed to something other than what I intended whenever I created it, is an attribute, not a detriment. So if you have some means in whatever language you end up working with to create something that is immutable, something that can assume values upon creation and guarantee that they will not change over the life of that object, then you know, learn how to use that. And then there will be cases where the state does get updated, where you do want to modify the state, and you won't use final or read-only or whatever modifier to create something immutable. That will come, but you know, in cases like this, then the name is never going to change during the life of it, right? Okay, so so again, this is one of those things where it seems like it would be something very primitive, something that you would learn early on and then disregard as you move further, but it's actually the opposite. This tendency towards immutability is something that's more of an advanced concept, but I want you to prepare yourself to adopt it and, you know, to use it, and make sure that whenever you don't finalize something or mark it as read-only or you know, as set once and then never change it again, that you intend for that. That is very purposeful, that you're allowing something to modify it. Right? And so it's even more protective than the private modifier, which guarantees that only stuff within the class can change it. This basically says only the constructor can do it. Okay. So whenever you create your edge, you pass in the name, the source vertex, the destination vertex, and then the weight. Okay. Those get assigned and they never change. And then we provide this public exposure that allows you know, whatever holds the instance of the edge to get its name. And then we can also view the source vertex or the destination vertex whenever we're traversing. And then we also provide a way to get the weight in a read-only fashion. Okay, so so now our toString for this, it's the name, and then we provide, you know, summary data for it. So the source vertex as a string, the destination vertex as a string, and then the weight as a number, right? And then a new line character, because we're nice to ourselves in that fashion. Okay, so now the graph class. So again, the package is Dijkstra, import java.util. We define the graph. The graph is defined as public, right? So it's the only thing that's actually exposed is public. And then it has the private variables, so the read-only hash map. And in this case, whenever you have some construct like this, right, it doesn't mean that that cannot be modified whenever you initialize it, right? So we initialize these hash maps, the vertices and the edges, right? These collections or dictionaries where we have the key and value pairs. And we can add to this, but we cannot change what we reference, right? So there is exactly one instance, and then we can act against the instance, right? We can add vertices to this, but we can't lose our reference, right? And that's exactly what we want. We don't want it to suddenly go missing, right? And so that these vertices, we end up building some new collection of vertices, and these edges all refer to some lost collection of vertices, right? Like that's completely useless to us. So in this way, right, by finalizing these, even though these objects themselves, the reference is immutable, the objects are not. We can still act against them and modify their state, which is exactly what we want. And by doing it in this fashion, we guarantee that this set of vertices will always be associated to the edges, or the edges that these refer to will always be that initial collection of vertices that we dealt with. And in such a case, you're like, okay, well, what if I need to modify the graph or whatever, come up with some new thing? Maybe I'm dealing with a spanning tree or something that I'm constructing from this graph. What do I do then? How do I modify the collection? Well, you create a new graph. Again, like I was saying, these aren't raw materials in the real world. For these things that are rare, such as whenever you would need to modify this, and you're not just adding a single vertex, or you're not building it up, it's extremely cheap to just construct something new and deal with that, and then you have these immutable structures that you're dealing with, right? So just keep that in the back of your mind. Okay. So whenever we initialize the graph, the only thing we really know is the name, and then everything else, as you'll see when we enter the main method, is going to build it up and then solve it, right? So first we define the collection of vertices, right? Because edges refer to vertices, so we need the vertices first, right? And so that's a series of vertex IDs, right? So we create the vertex. In this method, it takes the name, the vertex name, or the vertex ID in this case, and then it creates the instance, right? It places it in the hash map, and the key, the lookup key, is that name, that vertex name, or the vertex ID. Right? So it puts it in there, and then that's it. Right? It doesn't return anything. Right? It returns void. So it just adds it to its collection of vertices, and then you'll notice that we don't have an add edge, right? So how could anything add an edge if it doesn't have the reference to the vertex, right? So the way we add edges is by connecting vertices. Right? So we have some source and destination, right? And it's an undirected graph that we're discussing for Dijkstra's algorithm. So you could think of these as an unordered pair, right? But we'll still call them the same thing. It's left and right, source and destination, whatever, right? So vertex A and vertex B. And then that edge will have some weight associated to it. Right? So we get the vertices, right? We refer to it by that ID, right? So we get the first vertex, and then we ask our lookup to retrieve the second vertex based on that ID. And then the edge ID is we build it up from just however many edges there are in the collection, right? So E0 is the name of our first vertex or first edge. E1 is the name of the second one, and so on and so forth. And so we end up giving them the serial number beginning with 0. Right? And so this is just the way that we do that. Okay. So then now we add them to our hash map, our dictionary, our lookup, and the key is going to be that edge ID, right? And then the instance is created within the method, right? And so we pass it a name, a source vertex, a destination vertex, and a weight. Right? Okay, and then this is a thing that we have instances of. And so we provide this toString operator or method. So string builder. So this is another thing that is worth a moment of your time. Right? So I was saying that we don't modify things if we can avoid it. So it's fairly cheap to create new objects in any programming language, any modern programming language, against modern machines. But strings can be expensive whenever you're creating, thousands of them in rapid succession. So they are immutable objects themselves. So you create them, and then in order to prevent something called a buffer overflow vulnerability, so in order to make sure that you don't get hacked, we create a new instance every time a string is modified. So if you add something on to the end of a string, rather than seeing if there's space in some character array, we create a new string from scratch, and then in some managed language, or something with a runtime like Java or C# or whatever, then a garbage collector will run on a separate thread, and it'll go through and it'll say, okay, well, these objects are unreachable. I'll reclaim that space in memory, and then I'll reuse it later. But that happens later whenever the garbage collector has a chance to run. Until then, it takes up space in memory. And so you can get into trouble if you try to just concatenate values onto a string. So if you are building up a string of that's 1 kilobyte, then you have 1024 bytes, and you have 1024 operations. And if you're adding them onto the string one at a time, then you've created 1,000 strings, right? And only that very last one is the one that you actually hold a reference to, and the rest are just waiting to be garbage collected. And so they're pure expense in that regard. And so the way to avoid that, like if you want to build something up one character at a time, or if you're modifying the same content, what is intended to be a single string, right, and you don't actually want to create 1,000 instances of a string, then you use something called a string builder, and this exists in C# as well. I'm sure a fair number of other languages would also provide something analogous to it. In JavaScript, you would have to roll your own, I believe, but there may be a package for people that want something like that. You could put it in an array and then concatenate the array into a single thing, but even that, I'm not convinced is exactly what you want. JavaScript, I think you just gotta have to choke down all of those garbage strings. But anyway, in Java and C#, you can have a string builder, and then whenever you call toString, whenever it's fully ready, it'll take a look at all of the space that's necessary, and then it'll take a look at all the contents, and it'll create just one string instance. Right? So you do all of your appending, all of your concatenations using your reference. In this case, we called it SB, so sb.append. And so we begin with the name, right, and then it's got that new line character. And so this is our toString, right? So what do we want to see? So we want to see the name of our graph, and then we want to see the collection of vertices, right? So we say, okay, well, these are going to be the vertices, and we have our new line character. And then this is how you iterate a collection in Java. So we get our iterator instance. And we say, while it has next, while there's one more, then append vertex iterator.next. So whatever that instance is, whatever next was, whatever vertex that was, right? So next is going to be of the type that you pass in here. So the vertex is going to have, we defined a toString, so it'll implicitly call toString in order to add that to append. Right? And then whenever we run out of our vertex collection, then we add an empty line, and then we say, okay, we're going to print out the edges next. So here are the edges. We get an edge iterator, right, to iterate over the values of the edges. Right? And so while there's a next edge, then append that, right? And again, implicitly, we call edge.toString because append insists on having a string, and anywhere that you are coercing it into a string, it'll implicitly call the toString method, and if you haven't defined it yourself, then it's going to call whatever is there by default, and that's generally not helpful in debugging, right? So this is an added benefit of providing your toString method. And then once we've fully iterated over that, then we've added everything we're going to the string builder, so we can call toString and return that, right? And so then it'll jam all of that into a single string and it will return it. Okay, so now the main class. So it's again still in the Dijkstra package. It's public so that we can call main essentially. So it's defined as a static method, so we don't need an instance of the Dijkstra class. We can just call Dijkstra.main. But that's going to be done by if you compile it and run it from the command line, it will be done whenever you invoke it from the command line implicitly. Or if you run it from your IDE, like NetBeans or whatever, then it'll automatically invoke this, provided you don't have multiple entry points defined or something weird like that. Okay, so we invoke main, we create the new graph, and then we add the vertices, right, one at a time, A, B, C, D, and E, and then we connect the vertices. And then the version that I have attached in the lecture notes doesn't have invoke solve Dijkstra, so we'll have to take a look at that hopefully next time. But if I still don't have access to it, then it'll have to be the first class after spring break. We'll see. But that's how you set up the problem. So I would encourage you, take a look at the book, take a look at the pseudocode, and see what it's describing, and see if you can make sense of it. You have now, with that example, you have the ability to represent a graph programmatically, and so you have examples on how to iterate through the vertex collection and the edges collection. So how would you do it? How would you go through translating that pseudocode into functioning code? And so if I remember correctly, Dijkstra, it sorts the edges. It sorts by weight of the edges in ascending order. And then we're constructing a path, and so it says the shortest path is going to be the collection of, so you take the sorted edges, and then you pick the next edge, the next cheapest edge that doesn't create a closed loop, essentially, that still maintains something that could be considered a unique path, right? And so you start with the cheapest edges, and then if you start considering the heavier and heavier ones, and you throw out the ones that create that closed loop, and in the end you will get something that connects you from A to B in the cheapest fashion. Okay, so we'll take a look at that explicitly first chance we get. So either next time or the first class following spring break. For now, we'll just make a note on it. Right? So Dijkstra's algorithm uses on the order of n squared operations, where n is going to be the number of vertices. It's proportional to vertices. But edges can also be considered proportional to vertices as well. Right? So that's additions and comparisons to find the length of a shortest path between two vertices in a connected, simple, undirected, weighted graph with n vertices. A lot of modifiers on that. Okay, so the traveling salesperson problem. So this is what I meant when I said going from shortest path to shortest circuit or cheapest circuit is essentially a nightmare, right? So here it's n squared, and then here it's like on the order of n factorial, which we've showed is terrible, right? The log of n factorial is n log n, I believe, right? So it's the log of it is convex up or concave up, which is That's pretty bad. Okay. So a traveling salesperson wants to visit each of n cities exactly once and return to a starting point. What is the shortest way to do that? Right. And so you can think of this as a shipping problem. Right. So you have you're consuming some amount of gas to carry this extremely heavy product from A to B, and you can minimize your cost in gas in theory by minimizing the miles or the stop and go traffic and so forth. And so you have something that is able to tell you some cost, some weighted cost in the different routes from A to B, and you want to figure out, okay, well, what is the cheapest way to send this vehicle around and end up back where we started? And that problem is it is in you can always make your program worse, or there's always some more complicated problem so that you're dealing with this higher and higher runtime or more expensive runtime, and at the limit you have something that just never terminates. Right? But this is this is in the class of the first set of problems where in order to find the solution, not necessarily test for the solution, but finding the solution is no longer something that you can do or expect to do in polynomial time. And so if you want a polynomial time algorithm, then you need something that you need to approximate it. You need to deal for the fact that you won't get the absolute best solution, but you can do pretty well. Okay. You just have to kind of live with that, live with something less than the absolute optimal. And so it's an extremely interesting problem for that reason, because it is it's essentially that first level of worse than what we can hope to solve in some absolute sense. You just have to use heuristics and rules to try and get there. And that doesn't mean that the solution that you come up with isn't the absolute best solution. It just means that you weren't able to iterate over the entire collection of solutions to guarantee that it was the minimum. And it's because of the nature of this problem, right? So restated, right? This individual wishes to find the Hamilton circuit, so consuming vertices, of a simple, complete graph of minimum total weight. So every city is connected to every other city. Right? So if you have 32 cities, then each one has 31 roads out of it, right? Or is connected to the other 31. And then each one of those has a weight. And so how do you find the minimum weighted circuit? And the obvious answer is, okay, well, you consider every possibility, and then you sort them by weight, and whatever one's the minimum is the answer. And that naive approach turns out to, for 32 cities, to take several billion years to compute a solution, even if you parallelize it. So it's just too many possibilities to iterate over every one, and so you have to start hacking at it in different ways. Okay, so note that this is distinct from the solution provided by Dijkstra's algorithm, in which we ask for the shortest distance between distinct vertices for a fixed initial vertex. Right. So in Dijkstra, we're not trying to end up back where we started. We start at A and we're trying to get to B, and we want to know the shortest way there. Okay, so planar graphs. A graph is called planar if it can be drawn in the plane without any edges crossing, where a crossing of edges is the intersection of lines or arcs representing them at a point other than their common endpoint. Such a drawing is called a planar representation of the graph. Okay, so this is a definition. We're starting to consider this new concept of ways to of certain categories of graphs. And so a planar graph, you can think of it as being like something you would see on a map, right? Where the countries, if they have some non-zero border, right? So they connect at more than just a point. They have some stretch that connects them, right? So the four corners of Arizona, Utah, Colorado, and New Mexico. Right? The four corners, that's a border of 0 length between Utah and New Mexico, and the same between Colorado and Arizona. And so those would not connect each other. But if there is a strip, then you could represent them as a planar graph, right? And so in that case, the states would be the vertices, and the edges would just indicate that they border each other, right? So if they're connected, then they share a border. And so planar graphs is a way to reduce something that you would draw on a map, right, some cartographic representation, into something that we could deal with using programs, right? And so you would map it to this planar representation. And so, right, so the general category of that is planar graphs, right? And so we define them as these graphs where you can draw these edges between vertices, and if the vertices don't cross each other, or sorry, if the edges don't cross over each other, then it satisfies this requirement of a planar graph. And so, when you think of it in terms of a map, right, like a map of states or a map of countries or whatever, then it makes sense that you should be able to do this, that you should be able to connect these adjacent objects, right, these states or countries or whatever. And then, New York does not connect directly to California, right? There is no edge there, right? And so you don't have their edges crossing over because there is no shared border. Right? Okay, so those are planar graphs or planar representation. Right? So next definition, a planar representation of a graph splits the plane into regions, including an unbounded region. Okay. And this is where, if I had my whiteboard with me, I would show you, but we'll just make a note of that now. Right? And so you can think of this as if you're playing connect the dots, right, which is a planar representation. Right? Then once you've connected the dots, you can color in the regions between the lines, right, between those connections. Right? And then this last part, says the unbounded region. And so that would be the sky in your drawing or whatever, in your connected dot thing. It's just the rest of it, everything that's outside, that's not in the interior. Okay. So now we have a theorem. So not a definition, but a theorem. So given some graph, G, let it be connected, planar, simple graph with edges E and vertices V. Right? So a graph with edges and vertices, right? And it's both planar and simple. Right? And let R be the number of regions in a planar representation of the graph. Then we can compute R as the number of edges minus the number of vertices plus 2. Okay? This is like the number of different regions that you can color, using crowns on your connected dots picture. Okay. So corollary to that, if G is a connected planar simple graph with edges, with some number of edges and some number of vertices, and the number of vertices is greater than or is at least 3, and the number of edges, then in that case, the number of edges it has an upper bound of 3 times the number of vertices minus 6. Okay. So this says that in order to satisfy this planar requirement, that is where we don't cross edges, then there's this upper bound that we have to obey, and we can't have more than this number of edges or we violate the planar condition, that condition that the edges don't intersect each other. And so it's interesting to think that now we're starting to have these restrictions on the number of edges that we can have in proportion to the number of vertices. and that's because of the planar condition. And so if you have too many edges, eventually one of them is going to have to cross. And so this gives us the conditions that have to be satisfied in order for it to still be a planar simple graph. Okay, another corollary. If we have some graph G, and it's connected planar simple graph, then G has a vertex of degree not exceeding 5. And again, like it's another condition that says, okay, you can't clog up the number, you can't clog this thing up with too many edges. And so if you have a lot of edges on some of the vertices, then you need at least one that doesn't get too big, right? That doesn't exceed 5. Okay. So another corollary: if a connected planar simple graph has some number of edges and vertices, and we have at least 3 vertices, and no circuits of length 3, then the number of edges has an upper bound of twice the number of vertices minus 4. Right? And so as far as I can tell, this is just an interesting thing, an interesting property with no direct application. But you never know. You prove what you can in terms of what these limits are, and then you find out how to apply them later on. Okay, so again, this says that if you have some number of vertices, and you have at least 3 vertices, in this case, you don't have any circuits of length 3, so that you don't have it where the vertices are in these small clusters with one another. Then you end up with this upper bound for the number of edges. And this is even smaller. As V gets large, this is even smaller, right, than this initial upper bound. Okay, so now we have a definition. Right? If a graph is planar, then any graph obtained by removing an edge, right, which connects vertices U and V, and adding a new vertex W together with the edges UW and WV, such an operation is called an elementary subdivision. Okay, so if we go back to viewing this as a network, right, then this says that if you take a strip of cable and you split it and you add a booster in between, right, so you cut the line in half and you add some signal booster, then you haven't done anything, right? You haven't modified the graph in any significant way. You've taken one edge and you've broken it up into 2 halves, UW and WV, right? And so by definition, we call such an operation an elementary subdivision. And so you're adding vertices, and you're even increasing the number of edges, and yet you're not doing a whole lot. It's just this elementary subdivision, or you're boosting signal, if you want to think of it that way. Or on a highway, you're adding a gas station, right? Or a Buc-ee's or something, right? You're adding something that you could stop at, but it doesn't change anything in any fundamental way. Okay. So by definition, we have 2 graphs, G1 and G2. Each has their own collection of vertices and edges. We say that they're homeomorphic if they can be obtained from the same graph by a sequence of elementary subdivisions. And so you can think of this, you can think of one as, well, not even necessarily, right? You can think of them in a few different ways, right? So if you imagine this to be the initial graph, right, and then this is the one that evolves over time as you add all of these signal boosters, right? You identify places where there's a lot of drop packets, and you just have too much cabling, and information's getting lost. So you cut the cable in half and you add these signal boosters or whatever. Then this is the network evolved, right? And all we've done is perform these subdivisions. So even though we're adding vertices, it's really just in order to boost the signal. We haven't changed the graph at all. Then we say that they're homeomorphic. Okay, but this definition is broader than the example I've just given. So we could also consider G1 and G2 to be possibilities, right? So we start with some current state of affairs, some graph, call it G0, right? And it defines the network as it stands. Then G1 can be the proposals for the signal boosters in one scenario, and then G2 is an alternative proposal for signal boosters, right? So that they're related, they're homeomorphic with one another, right? But they don't necessarily evolve from one or another, right? They can just be these two alternatives, right? And in such a case, they're still homeomorphic. And we could, if you go in the opposite direction, right? So what this says is that if you go to the opposite direction and you remove all of these elementary subdivisions, that you take these edges, which are just a logical split of some root edge, some longer edge, then if you go in that reverse direction for both of these graphs, then you end up with some common graph, right? So they can be obtained from the same graph, right, by a sequence of elementary subdivisions. Right? Okay, so that's homeomorphic. Okay, so a graph is non-planar. This is by theorem. A graph, and I think that last one was definition. Yes. A graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. Okay, so well, it's a little hard because I don't have this drawn. I should really add that to the notes. But K33, if you remember the example of a bipartite graph, right, where we have these dancers that we're pairing off, right? I think we used the Dancing with the Stars example or whatever, where you have professional dancers and amateur dancers, and you don't pair professionals with professionals or amateurs with amateurs. You take one and you pair it with the other, right? And so that was the bipartite example. So K33 is the bipartite example, where you have 3 vertices in the top line and 3 vertices in the bottom line, and then they're fully connected with one another, right? And then K5, I believe, is a complete graph with 5 vertices resembling a 5-pointed star. Right? K33 is a bipartite graph with 3 vertices in each partition. Right? And so this says that a graph is non-planar if and only if it contains a subgraph homeomorphic to these. Right? So you can do those elementary subdivisions, but at its root, or in principle, these are the 2 violations, and the only 2 violations, the only 2 unique violations that would make a graph non-planar, right? So if it contains one of these, then it is non-planar, right? If this is a subgraph, then, or something homeomorphic to it is a subgraph of this, or has these as a subgraph, then it's non-planar. And vice versa. If it's non-planar, if you're given that it's non-planar, then you know that somewhere in there is a homeomorphism to either the K33, the bipartite graph, or the 5-pointed star. Right? Okay. Let's see if we can finish this section, and then we'll call it a day. Okay, so next definition. A dual graph is a planar graph constructed from the regions of a planar map. So the regions of the map become the vertices of the graph. 2 regions are considered adjacent, hence are connected by an edge if they share a border of length greater than 0. Note that 2 regions are not considered adjacent if they connect on a point. For example, New Mexico and Utah on a map of the United States. Right. So this is what I was talking about before. So if you have this association, right, between a map and a graph, a planar map and a planar graph, then you have something called a dual graph. So it has this dual representation, right? Both as a map and as a, in computer science, what we've been calling a graph. Right? And so it's exactly what I was saying earlier. So the states, or the counties, or the countries, whatever that show up on the map, these regions on the map, become vertices whenever you're discussing them in terms of the computer science graph. And then they share an edge if they have a border of length greater than 0. Okay, so that's a definition. Next definition. The coloring of a simple graph is the assignment of a color to each vertex of the graph, so that no two adjacent vertices are assigned the same color. So now we can discuss this topic of coloring a map, right? By dealing with its dual representation as a planar graph. The chromatic number of a graph is the least number of colors needed for a coloring of this graph. The chromatic number of a graph G is denoted by chi of G. And then theorem, the chromatic number of a planar graph is no greater than 4. So you can color any dual graph, or any dual graph with no more than 4 colors if you so desire, which is interesting. So I will leave it up to you to find examples of where that's terribly beneficial, but it is an interesting result. But I think its greatest point of interest is this idea that you can go back and forth between something that takes up space in terms of regions, like counties on a map, and map it to something constructed of points and edges, like the logical graphs that we've been discussing, the data type of a graph. So I think that's cooler than the theorem, but the theorem on its own is an interesting result. Okay, so example applications of graph coloring. How can the final exams at a university be scheduled so that no student has 2 exams at the same time? And so the answer is to model the problem by defining the courses to represent the vertices. An edge is drawn between 2 vertices, or 2 courses, that is, if there is at least one student in common between the 2 courses. The colors represent the time slots themselves. So the number of colors necessary to color the non-planar graph indicates the number of time slots necessary to schedule all exams. And so this is another way to think about these problems. And so using these abstract data structures that we've been discussing in order to solve practical problems in the real world. And so that is, I think that's really interesting too. Okay, trees. Well, let's save it for next time. Okay, well, have a great evening. One more lecture until spring break, and hopefully that'll finish up these notes as well, and we can start doing even cooler stuff after the break. All right, have a good evening.